Welcome, everyone. Good morning, good afternoon, good evening, wherever you currently are. It's a pleasure to welcome you to the second edition of this term's IRENA online seminar. 2 weeks ago, Lorenzo Lomberti gave a seminar on carbon-oxygen shell mergers in massive stars. And today's seminar will be dedicated to the direct detection of ejected radionuclei here on Earth using Accelerator Mass Spectrometry. Our guest speaker today is Dominik Koll. It's a pleasure to quickly introduce him to you. Dominik studied nuclear and particle and astrophysics at the TU Munich here in Germany and graduated with high distinction. He then pursued a dual PhD at the Institute for Nuclear and Particle Physics of TU Dresden and the Australian National University, where he also got a prize for the best PhD thesis in physics. He obtained his PhD with summa cum laude in 2023 and is now working at the Helmholtz-Zentrum Dresden-Rossendorf. As the title, which you currently do not see, might suggest, his research focuses on the detection of long-lived radionuclei in the environment using accelerator mass spectrometry, and I'm really looking forward to your seminar. Dominik, it's a pleasure to have you here, and the stage is yours.
Thank you, Stefan, and also for the invitation. And I'll quickly share my screen and hopefully everything works. Let's see, it should be this one here. So, can you see the screen?
Yes, perfect.
Perfect. Okay, yeah, then, yeah, I would say time's to start. Yeah, thanks again for the introduction, also for the invitation. It's a pleasure to speak about my favorite topic, namely the search for radionuclides from stellar explosions on Earth. And I'm fully aware that this topic is quite niche and you might not be familiar with it. So I want to set the stage and start a bit slow to yeah, take you all on board on our journey through space and through Earth's geological history. So yeah, we start on Earth, and on Earth, well, near Earth, there might be a massive star. And the massive star undergoes its life cycle, and at the very end of the life, it will undergo a so-called core collapse supernova, which is essentially a very big explosion. And for us, these explosions are quite interesting because depending on how far away they are, they might be interesting to us because we might observe them or might even get a little bit from them onto Earth. And I try to depict it in a way everybody understands it. If it's too far away, we are quite unhappy because we have nothing from the supernova. If it's too close, we are really unhappy because we might be blown away. And usually we are quite happy if it's in an intermediate region, typically on the order of 30 to 100 parsecs. And these supernovae, well, they are known to eject their material into space. This can be plasma, this can be cosmic rays, neutrinos, but also tiny, tiny dust particles. So supernovae are known to be dust factories, and these newly produced radionuclides, they can be incorporated into dust through condensation. And now if it's just close enough to Earth, we might have a chance that either we get a little bit of this dust moving towards us and Earth incorporates it into its geological cycle, or the dust is sitting around in the interstellar medium and Earth picks it up by moving through some sort of cloud of dust. And the big question is now, of course, how do we identify the dust particles of being of interstellar origin? And we do this by their radioisotope signature. And there's a certain number of radioisotopes that are produced in supernovae. The number is quite large, and we need to make the decision which one to look for. And for this, we have some sort of criteria. And the first criteria is, of course, it has to be produced in stars. The second one is it has to live long enough to make its travel from the stellar explosion towards Earth, which is on the order of hundreds of thousands of years. So we're talking about half-lives that should be above the hundreds of thousands of year range, typically in the million-year range. And it shouldn't be present on Earth. So that ideally, these radionuclides are not present on Earth by any means, so neither from primordial sources nor from cosmogenic production. So that when we find it on Earth, it's a clear signal that it has to come from a supernova. And for this, we have a suite of different radionuclides that fulfill some or all of the criteria. And in our case, aluminium-26 is also present on Earth through cosmogenic production, so we usually don't take this one. Manganese-53 is produced by cosmic rays in interplanetary dust, so we also have some sort of a fraction of manganese-53 on Earth. And hafnium-182 is produced in small quantities in stellar explosions or in an R process or an S process site. And the chemistry and the measurement is very tricky for hafnium-182, I can tell you. So usually we stay with these three here, and the one is the iron-60, which is a very typical core collapse supernova signature, and plutonium-244 and curium-247. These are our processed radionuclide, and this essentially defines what we can, what the scope of our investigation is. First is we check supernovae and the R process and want to see if supernovae contribute to an R process abundance in the universe, or if they just act as distributors of material that is already present from previous R processes sites, which could be rare, like a neutron star merger. On the other side, by having two R process radionuclides with different half-lives, we can use them as a sort of chronometer, because we know more or less how much of plutonium and curium is produced in an R process event. And then by the radioactive decay, we might be able to date when the R process actually happened. And that is what we're trying to do in our work. So you might rightfully say, well, it's a nice story, but is there any chance to measure one of these radionuclides at all on Earth? So is it present near Earth? And the answer is yes. So for iron-60, we know it's, for example, present in the cosmic ray spectrum. So for example, here, Binz et al., they measured cosmic rays near Earth, and here are the iron isotopes depicted, and you see a very small signal of iron-60, and these are high energy cosmic rays. On the other side, we also know from spectroscopy and on satellites that iron-60 is in the galaxy and decays, and we see its decay radiation. And that has been known for a very long time, and is actually a clear indicator that nucleosynthesis is ongoing in our galaxy. So that means iron-60 is certainly around us, but I want to really highlight that we are not looking for the decay, we are not looking for the cosmic rays, we are really looking for this condensed dust particles, because they eventually make it into the solar system rather undisturbed because of their high mass and relatively high velocity. So they follow a rather straight trajectory and might then come to Earth. All right, so the question is, okay, what could we learn by finding iron-60 or the other radionuclides? And for this, we need to look at the solar neighborhood. So we live in our galaxy, in the Milky Way, in one of our spiral arms. And if we take a closer look, our solar system is within a void, which is called the local bubble. And this local bubble here depicted in dark, these are less dense regions. The blue here is a bit denser. And this local bubble naturally looks like as it would have been formed from a supernova explosion. It looks like it was pushed out, material was pushed out to the rims by one or many more supernova explosions in the past. And of course, we might be able to find traces from these supernovae still in our geological record. If you take an even closer look, then we would see that inside of this local bubble, which is rather empty, we see substructures, and one of these substructures is the so-called local interstellar cloud or local fluff. And it is believed that these local interstellar clouds or these cloudlets here, they also might be remnants or might have been formed by supernovae, where you have dust clouds that fragment and then they condensate together, and then you have these substructures in this void. And if it's true, then of course these cloudlets might be archives of radionuclides ejected by supernovae. So, but that's a very narrow range around the solar system, and Here we are talking about timescales to be investigated on the order of tens of kiloyears, whereas if you want to investigate the local bubble, we are talking about millions of years. All right, so now the question is, okay, where do you want to look for that on Earth? And the basic example would be, oh, you go to to the continents and you just check on the floor, like on the ground, do you see any stardust in there? And the answer is no, because stardust comes in very tiny amounts, and the regular ground has way too much geology, or to phrase it simpler, way too much dirt. It's not easy to find the stardust and the radionuclide signature just on the continent. So you need very special samples. And there are essentially two ways and two sites on Earth where you can detect stardust, or which are promising sites to detect stardust. And that is the deep ocean, because the deep ocean stores the stardust over long times, the polar regions, because they are really pure. And then if you leave Earth, of course, then you have the moon, which has no geology going on and stores radionuclides for a very, very long time. And that essentially defines the samples we need to look for and need to obtain to do our measurements. Then from the samples to the question on how do you measure that? Well, the search for these radionuclides, I mean, you could do decay counting, but the problem is, since this the half-lives on the order of millions of years or even longer, it's just simply not effective to do decay counting. You would measure forever, and the activities are so low that you essentially cannot measure it. So, and the background is just killing you. So decay counting is really not the option for this type of searches, because in the end you want to measure single atoms in dust. So if it's not decay counting, the better option, of course, is to measure not the decay of the radionuclides, but to measure the radionuclides directly. And this is then counting of atoms, and this is called then mass spectrometry. And there is a vast number of different mass spectrometry techniques. SIMS, which is secondary ion mass spectrometry, TIMS, which is thermal ionization mass spectrometry, RIMS is resonance ionization mass spectrometry, and ICP-MS is inductively coupled plasma mass spectrometry. And they all have in common that they are mass spectrometry techniques indicated by the MS, and the letters in front of the MS essentially determine only how you produce your ions. The problem of all of them is they are not sensitive enough because they have some molecular and isobaric interferences. And I want to show you what I mean by that. So this is a sketch of a mass spectrum you would encounter when you look for iron-60, for example. So iron-60, the intensity you want to measure, so the amount of atoms is very low and is completely burned and overshadowed by all different other isotopes and molecules. So for example, you can have a molecule from something which has a completely different mass, but by molecular combination it gets the right mass compared to iron-60, so it falls into the iron-60 region. Or you have a stable isobar, has the same mass but is stable compared to the radionuclide, and nickel-60 is abundant in the environment. Or you have something which is really intense but has not the right mass, but its tail goes into the region of interest of iron-60. And this looks now like a problem. Oh, well, we're talking about some factors we need to get rid of in the sense of background. But this really means here getting 10 orders of magnitude away, because, for example, nickel is 10 orders of magnitude more abundant than typical iron-60 in our sample. And this is already for chemically purified samples. The best chemistry we can do to get rid of the nickel still leaves us with 10 orders of magnitude we need to suppress until we can measure single atoms of iron-60. And this is really a big challenge, and you need a very, very sensitive measurement technique that is able to resolve these 10 orders of magnitude. And there is essentially only one technique capable of doing that, and that is accelerator mass spectrometry. For accelerator mass spectrometry, you're using different facilities. As an example, I brought you a picture of the facility I'm working on right now. So that's the DREAMS facility in Dresden at the Helmholtz Center. And we will get a new machine, or actually we got already, we're just about to start measuring there because we were setting it up the last couple of weeks and months. And that is going to be called Hamster. And I invite you to check out our webpage to see the progress on our new machine. And I think you might be curious on how do you get rid of these 10 orders of magnitude now. And I don't want to leave you hanging. I want to show you how to do it and how AMS actually works. So this is a typical layout of an AMS system. And as you can see, you have essentially three parts of an AMS system. You have a mass spectrometry part, a mass spectrometer on the low energy side, on the high energy side, coupled by an accelerator. And as you can see, there are only a few basic elements in there. So AMS, to understand AMS is rather simple, but of course, the problem lies in the details to get rid of really of this 10 orders of magnitude. So how does it work in the end? You start by a cesium sputter ion source, so you have samples in a sample wheel, and you put it into an ion source and you form a negative ion beam. And then you start mass filtering on your low energy side. But the problem still is you still fight against all the molecules and the isobars with the same mass. You can't get rid of them. But then you have our nice accelerator. And the accelerator not only provides us with higher energies to make the detection more easily, but it also does a stripping process. And it changes the negative ions to positive ions. And that really does the trick, because the molecules are bound together by electrons. And by taking away the electrons and making your ions positive, you really break up the molecules. And after the molecules are broken up, you just need another mass filtering step on the high energy side here to get rid of them. And you're left with just atomic ions. And if your filters are strong enough, you get a pure signal out of it. So you have momentum filters, you have energy filters. Usually you use duplicates of them to just be more sensitive and more powerful in the filtering. And in the end, you have a particle detection system, typically an ionization chamber, that gives you a signal that, for example, for beryllium-10 and boron-10 looks like that. And you can see that you can distinguish between two isobars, and there is no molecular fragments in the spectrum anymore. And that's how you clean up your signal. And this sounds all really, really nice. And I want to show you even clearer that it really works the way I described it by describing the ion beam by its properties. So an ion beam can have a mass, an energy, a velocity, momentum, nuclear and electric charge. But you can get rid of some of them because, well, they depend on to each other. So, for example, we can get rid of the mass and the momentum. The nuclear charge is rather inaccessible for us in the whole spectrometer, because only at the very last stage when we do the energy and energy loss measurement in the ionization chamber, the nuclear charge is revealed. So in the end, we are left in our spectrometer with the energy, the velocity, and the electric charge of our ion. And you can plot it in this velocity and energy divided by charge diagram. And now I put one filter after another in to show you how we filter out all our unwanted isotopes. So for example, if you have a magnet, the magnet is a momentum filter, and the formula gives us that E over Q is proportional to V. So that's essentially this behavior here. And we filter along this line. Then we use an electrostatic analyzer. So that's an energy filter. These are just high voltage plates. And this is sensitive to the energy over charge, which needs to be constant in our system. So that's this line here. And as you can see, we have one crossing already. And that's the crossing where we set our system and tune it to the mass of interest, so the isotope of interest. In our case, iron-60, it could be plutonium-244, could be curium-247. We can further purify our sample by having a velocity filter, like a beam filter, where velocity is then set constant. And as you can see, they all work together, that you really narrow down your degrees of freedom, or your energy divided by charge, and your velocity. And in the end, you really end up by a highly purified ion beam that can be then analyzed in your final particle detector. And this is highly efficient, except for the isobars. So the isobars, they have the same mass over charge ratio, because this here, energy over charge and velocity, in the end, the whole filters all together, they are only sensitive to an M over Q ratio. So everything that has the same m over q will make it till the very end, and we need to then distinguish between the different isobars. So the one isobar, like the molecules, we get rid of in our accelerator, I showed you before. So that's already very powerful, and that makes AMS really more powerful than the other mass spectrometry techniques where they fight against these molecules till the very end. We get rid of them. But nevertheless, we are left with these atomic isobars. And they, in the end, therefore, we need also the accelerator to provide energy, because in the end, by energy loss measurements in our ionization chamber, we track the energy loss behavior to the Bragg curve of the two different isotopes, the two different elements. And since they have a different proton number, they lose energy in a different way. And we can, by having a segmented anode, we can have a segmented energy loss signal here, and we can follow and track this curve and then determine if it was an iron or a nickel-60 isotope. And this is really, really, really powerful. So in the end, we get away, or we get rid of all the nickel-60, these 10 orders of magnitude, and we are left with pure iron-60 counts in our detector, and we can check also if everything is set for iron. So if there is a nickel-60 coming through, we can distinguish it by this energy loss measurement. And this is rather clear, and it makes our system and our measurement capability very powerful and more powerful than the other techniques. Right, so these were the basics. So we know what to look for, where to look for, and how to look for it. So now the question is, what did we do in the past, and what's the current state of our research? And first, a short history of the research field. And it all started in 1996, where a couple of radionuclides were proposed to be promising signatures of a nearby supernova, and it turned out that iron-60 is actually the best tracer to study on Earth, because all the others, they have either terrestrial background or the measurement is very difficult. So iron-60 is the tracer for the study of stardust on Earth. And then followed a couple of years later, the first discovery of supernova iron-60 was announced. And also it was already searched for plutonium-244, however, no plutonium was found yet. I want to show you the iron-60 data, how it looked like. So they were looking for iron-60 in a deep ocean ferromanganese crust. And I will tell you later what this actually is, because these ferromanganese crusts, they follow our research through and through. So what they did is they measured an iron-60 to iron concentration over time in this crust. So this crust has, well, they took a depth profile, and it can be translated into an age profile. I will explain later how this is done. And what they found is that they saw a lot of background background signal in the detector, but around 2 to 3 mega years ago, they saw an enhancement of iron-60, and they interpreted back in the days as being iron-60 coming from a supernova to Earth. This, of course, well, was a sensational claim, which required a bit more proof, which was then done in the following years. Then in 2015, they tried again for plutonium-244, and they got an upper limit. They didn't detect anything, but nevertheless, it was already competitive enough to exclude just regular supernovae as being the dominant source of our process radionuclides. And in 2016, this was really the year of iron-60 detections. So they found iron-60 in sediments, in deep ocean crusts, in nodules, and on the moon. And I want to show you, for example, the data in the moon. Here they measured the iron-60 with respect to another radionuclide, manganese-53. This is dominantly produced by cosmic rays. And in gray, that's the band you would expect from cosmogenic production by cosmic rays. And you see some data actually falls onto this line. So there's no surplus of iron-60, but they saw a clear surplus of iron-60 in some samples. And if you do the calculation how much it is, it actually fits very nicely to the deep ocean sample. So this all fits very nicely together to this 2 to 3 mega year old iron-60 signal. Then after that, the question was, okay, million-year-old signals, but what about today? Is there a chance to measure iron-60 today? Is there iron-60 coming to Earth even today? And the answer is yes. That's where I jumped in. I was looking for iron-60 in 500 kilograms, half a ton of Antarctic snow. And again, we found a surplus of iron-60. Here again, that's a similar plot to the lunar samples. Here in red, that's the cosmogenic prediction. And here, these are all meteorite samples we measured. And as you can see, they all fall very close to the prediction. The prediction is independent of the data. It's just a nuclear cascade model that was developed for cosmogenic production of both radionuclides. And we see about a 2 order of magnitude enhancement of iron-60 compared to manganese-53 in our sample. The most likely nickel to iron ratio that determines the cosmogenic production is around 0.05. That is essentially chondritic material. So that's a clear enhancement of iron-60 and tells us that there's still iron-60 coming to Earth right now. And I want to just mention as a side remark, side note, a very nice discussion we had at the Carpathian Summer School of Physics this year, where I met the famous Carlos Bertolani, and he made a really nice statement that I kept in my mind, and that is, forget Nature papers, aim for the New York Times. The New York Times is way more interesting than Nature papers. And we actually made it. So this signal here was reported in the New York Times, and I was actually quite pleased that Carlos made this statement. It was quite curious and funny. All right, so and what do we learn actually from this iron-60 still coming to Earth today? Well, going back to this graph here, I told you that we, if these clouds are actually produced by supernovae, or have seen some supernova activity in the past, they might store the iron-60 from that time. And now the only question is it really the iron-60 we're seeing now coming from this local interstellar cloud? And to investigate that, we would need to look for times where we've been inside and outside the cloud. And if we see a difference in iron-60 influx between these two timescales, we would then know if the local interstellar cloud is the source of the iron-60. And we are working on that, and hopefully we will have a paper on that coming out soon. Measurements are completed. We did again an ice core from Antarctica, which is about 60,000 years old, and that's outside this, outside the time scale where we've been in the local interstellar cloud. So paper is soon coming out, and hopefully you will have nice news coming out, well, in the next half year or so. All right, so this is not the end of the story, because in 2021, actually also plutonium-244 was found for the very first time. And that was really a very nice discovery, because it took much longer for plutonium to be discovered compared to iron-60. And the reason for this is it's just way more difficult to measure plutonium-244, because compared to iron-60, it is about 5 orders of magnitude less abundant on Earth. So you need an even more sensitive measurement and efficient measurement to find traces of plutonium-244 on Earth. So the iron-60, as you can see, you will get really nice signals now over time, over millions of years. But for plutonium-244, we only get rather broad signals. And this is simply because we need to put together a large sample mass to overcome these 5 orders of magnitude. So you don't get this nice time resolution. But to investigate now if the plutonium and the iron-60 are produced in the same site or are actually transported by supernovae, you need essentially similar time resolution to see if the plutonium is really transported together with the iron-60 or was produced together with the iron-60. I also want to mention a very recent study. So a group in Romania, they analyzed so-called stromatolites. These are essentially fossilized bacteria in lakes in Africa. And they also investigated plutonium-244 and found a very weak signal there, however, with no sufficient time resolution or time profile. But nevertheless, it's compatible with the work from Wallner et al. And if you take everything together, this all is compatible with plutonium-234 either being produced in very low amounts from supernovae or being transported together by the blast wave of the supernovae. And what I want to do is I want to go deeper into that and want to see if this is really true, if the plutonium is either produced in the supernova or transported together with the iron-60. And for this you need better time resolution. And that was essentially my main task for my PhD work a couple of years ago. You might rightfully ask, okay, which sample did you take? Which sample do you want to use? And the answer is, of course, again, these very nice deep ocean ferromanganese crust. And now it's time to explain to you what these actually are. So these deep ocean ferromanganese crusts, they can be found in all major oceans on Earth. So these are very common things to appear. And here you can see the ocean floor is actually covered in these ferromanganese crusts and nodules. And the way they form is by precipitation out of seawater. So you have colloid formation, minerals are dissolved in seawater, and at some point, because of the very high pressures and the chemical conditions down there, they precipitate out of seawater and form rock layers onto basaltic rocks, mostly on basaltic seamounts that have no sediment coverage. You can imagine that this process is very similar to stalactites and stalagmites in dripstone caves, just the whole thing happens underwater. The beauty of these samples is they grow really, really slowly. This process is one of the slowest on Earth. The growth rates of these samples are millimeters per million of years. And this makes these samples so special because in a couple of centimeter thick samples, you cover tens of millions of years of geological history. And since they incorporate everything from the seawater, of course, any radionuclide that is present either from cosmogenic production or from nuclear weapons testings or also from astrophysical sites, they get incorporated into these samples. So they are really very nice radionuclide archives over a very long time scale. This is a picture of a ferromanganese nodule. So for the nodules, I just go back. The nodules are typically in the sediment and are sitting on top of the sediments. And if you cut them open, you see they have a very interesting structure. So they almost look like cauliflowers on the outside. In the inside, they often grow around a nucleus. This could be a little rock fragment. It could also be a shark tooth. It could be a little a fish bone or anything hard, and they start growing on that. But these nodules, they are not as nice as ferromanganese crust samples because they grow, as you can see, in a very irregular shape and in an irregular way. And if you want to have a really nice time profile, you don't want to have these irregularities. You want to have a flat sample that grows in nice layers on top of each other. And for this, we take ferromanganese crusts because they actually do exactly this. And for my study, I had the ferromanganese crust called VA13. It's actually one of the best studied crusts in the world we have. So they're almost all radionuclides that can be measured in this crust were measured already in the past since the 70s when it was retrieved. And for my study, I paid attention to do a lot of characterization of this crust, because as you can imagine, if you want to get really nice time resolution on your data, you need to understand the growth of this sample. Because it's a natural sample, there might be irregularities, inhomogeneities, and that's why understanding your sample is key to get good radionuclide data in the end. So what I did is I did an optical scan, as you can see here, and you can see that the crust has different structures on different sides. And for the low mass radionuclides, beryllium-10, aluminium-26, manganese, and iron, I did drill hole samples on 3 different locations to also see if there are any spatial differences in the sample. For us, important is that I used in the end the same sample for beryllium-10, which I will use for dating of the crust, and for iron-60 for our interstellar radionuclide signature. And this is really critical because now the dating and the iron-60 data is fully comparable because it comes from the same sample. And that was not done before in this way. Usually you take a drill hole for the dating and you take another drill hole for the iron-60 data. And then you need to somehow merge them together and fit them together. But in this case, for the very first time, the radionuclide dating and the iron-60 data is fully comparable because it comes from the same sample. For plutonium-244 and curium-247, however, you need not only drill holes, but the whole samples in layers. As you told you before, there's a 5 order of magnitude discrepancy between iron-60 and plutonium-244. So you need just way more sample to be able to measure plutonium and curium. Curium was not measured before, so it's going to be the first time that curium-247 is measured. And again, the same plutonium and curium is extracted from the same sample. So both radionuclides will be fully comparable. And that is critical, of course, because when we want to use them as a chronometer, it's again important that they are fully comparable and fit together, and that there is no question about the relation between these two in the sample. So I did, as I said, the optical scan. We also did an X-ray scan, which revealed some inner structure. And as you can see here in this picture from the micro CT scan from the tomography, you can see that there are lighter regions and darker regions. And this resembles essentially the same effect as tree rings in a tree. So these are growth layers of the crust. And these growth layers here, as you can see, they are not flat at all. They rather follow the surface geometry to a certain extent. And now, back in the days, what they did is they took the sample and cut them into pieces by hand without knowing any structure in there and without knowing any growth layers. And that's why the time resolution was never that good in previous samples, because it was never accounted for these growth layers here, for this behavior, for this bent shape. But this time really made sure to have a good understanding of the growth. That's why I also did beryllium-10 dating on our samples, and not only in one drill hole, but in 2 drill holes that were laterally separate by about 20 centimeters in our samples, and clearly in different regions. Here it's rather flat, here it's rather irregular. These are called botryoids. These are actually common features in the ferromanganese crust. And the beryllium-10 profile, beryllium-10 is produced in the atmosphere by cosmic rays and then incorporated, and the decay of beryllium-10 with a half-life of 1.4 mega years can be used for dating. And as you can see, you have here 2 profiles that deviate from each other, and that is exactly what you would expect from this behavior here, from this bent structure and having drill holes at different locations. So the age does not correspond to the same depth in the crust, and that's exactly this bent nature, and you need to account for that. This is the critical bit to get time resolved data. As you can see, also you have different growth periods. So here it was growing a bit quicker, a bit slower actually than here. That's why the decay is a bit faster in depth and rather than here. And these are all things you really need to account for to get good time resolved data. Because we got all these nice radionuclide data from the dating plus the CT scan data, we were then able to computer model the growth layers of this crust. That was the first time that it was done in a computer model way. And this, of course, allowed them to collect our samples for the plutonium in a computer-controlled machine way. And again, before it was done by hand, this is now done fully computer-controlled. The accuracy is expected to be much higher. Well, expected does not mean it necessarily is that way. So I wanted to check my large layers where I take my plutonium and curium out of it, compared to my drill hole sample, and see if the dating matches and if it fits together and you really get nice accurate data. And I can tell you it's amazing. So the large layers here in green, they perfectly fit the drill hole expectation. So we are very confident now that the dating and the layer generation of our crust is is perfect, and we get very nice time-resolved data for the iron-60, but also for the plutonium and the curium-247. So with this, everything was ready to start our measuring campaign for the interstellar radionuclides. I want to remind you, this was the previous data set from 2004. As you can see, the enhancement here. This was measured in Munich. In our case now, I measured it at the Australian National University. Here, this is the accelerator tower. The tower, well, the accelerator is vertical in the tower. The tower is 20 meters high, and the whole facility is located at the nice Lake Burley Griffin and Black Mountain in the middle of the city of Canberra. And I want to show you now how we improved the measurement from 2004, now about 15 to 20 years later. And as you can see, the method clearly improved and our sensitivity clearly improved. We see now the background here, which was about an order of magnitude higher back in the days, is now so low that we can resolve two influxes very clearly with high statistical confidence. The first one fits very nicely to the data we got here, but now we see also the second influx that was previously found also in the study of Walner et al. In 2021. This is, of course, the measured data, tells us about the iron-60 that is present in our sample, but of course we want to know how much iron-60 came to Earth at the time when the iron-60 arrived. So you need to do a decay correction, and that's why also, again, the dating is so important, because the decay correction depends on the dating. And the true story looks like this then. You have the peak now very clearly at 2.4 megayears. We could constrain the dating of this peak now even better than before. And the second peak here now is clearly resolved above the background level. And the dating of the peak was, well, a matter of discussion previously, because the previous two studies that found once an indication for the peak and once a clear signal of the peak, they were discrepant. So they were not entirely in agreement where they would put the peak. So these were the two intervals that were finding the peak. And now, taking the new data in, we can now put the peak influx at 7.2 megayears. And this is, of course, very critical input for the astrophysical modelers that want to look for the source of the iron-60 in our local bubble or the solar neighborhood. And the 7.2 megayears, they would rather point towards that we have been outside the local bubbles, in the outside region. Whereas for the 2.4 megayears, we have been inside the local bubble. And this would mean that these two iron-60 signals would then actually sample or be signatures of different regions of our solar neighborhood. And the astrophysics modelers, they are currently working on well, a better understanding on where the iron-60 was produced and how these two signals could appear on Earth. Because there's still the matter of question if the second signal could also be due to the transition through this edge of the local bubble. But this is a work in progress. Last but not least, let's go to the actinides, to the plutonium and the curium. For the plutonium, we went into a strategic partnership with the Australian Nuclear Science and Technology Organization in Sydney. Here you can see the photo of the Helmholtz Zentrum Dresden-Rossendorf director and our group leader, Tony, together with the people from ANSTO, where they were all happy signing our memorandum of understanding. And we went there because they have currently the highest sensitivity for actinide measurements in the world. As I told you before, the time resolution now is much better than before. Now we are on the order of 1 megayear per data point. Previously, they've been on the order of 5 megayears. And in the very first study, where they only got an upper limit, it was on the order of 20 megayears. So we tremendously increased our time resolution and now are capable to resolve the plutonium influx as well as the iron-60 influx. The sensitivity we reached is 1 out of 90 atoms. So this is really something you need to get your head around. you only 90 atoms in your sample and you detect one in your detector. So translating it to a concentration sensitivity, that would be 1.4 septogram per gram. An extraordinarily high sensitivity, which is direly required to be able to measure plutonium-244 on Earth. So what we found is we found a bit less plutonium-244 compared to the previous study, which is, well, you could expect that there are differences because of geographical, geological, and environmental reasons. In the end, these are different environmental samples, so the absolute amounts might be a bit different. And we know how to correct for that. But now we have the time resolution, and the time profile is the interesting bit. And what we see is, whereas for the first iron 60 peak here, the plutonium-244 intriguingly would be high and would be up. For the second one, it isn't at all. So it rather almost looks like it is anti-correlated. So we certainly can constrain the plutonium yield in iron 60 core collapse supernovae, because they would be if they would be produced on the same site, they would be transported together to Earth. And if you look at the spectrum, or at the distribution of the plutonium, the error bars are here, they are rather large, but the rest of the data, it looks amazingly flat with not much structure in the data. And I was thinking about it, okay, how could you explain something that you get a really flat behavior of the plutonium, whereas the iron 60 clearly is modulated and coming from the supernovae. And my idea was maybe the plutonium is just really, really old, and you have many supernovae going off over millions and tens of millions, maybe hundreds of millions of years. And they just push around and distribute the plutonium in such a way that you have, let's call it a plutonium fog in the solar neighborhood. And there's just plutonium distributed all over the place. Now the question is, how can we prove that? And this hypothesis would not be able to prove with plutonium alone, but now we have the curium-247 as being the chronometer. So we can now look for how old is this plutonium actually. Because if it would be from supernovae, it must be rather young, because supernovae go off rather regularly. But if it was a really old source, my idea could be correct. So we measured the curium-247. Again, that's also interesting to note. The time resolved data from before, let me just quickly go back. The time resolved data looks different to the study before, but only because these are single data points. Once you combine it at the similar time scale, it remarkably reflects the data from the study before. So the trends are very much the same. And this gave us confidence that our measurements are actually true, and that the signal is also a rather global signal, because these are different samples from different locations on Earth. So we find the same behavior in different samples, but now, of course, with the higher time resolution, we see substructures in there, which was not be able to see before with these broader time intervals. But now, yeah, let's go to the curium-247. We went back to ANSTO, because also there for curium, they have the highest sensitivity. Time resolution is the same as for the plutonium, because they were extracted from the same sample. But now the efficiency is even better, because the curium forms more readily an ion beam than plutonium does. So we have now a sensitivity of 1 out of 50 atoms, which when you then take together our sample, and for curium we still need to combine a bit more samples, because curium is even rarer than plutonium. This then translates to 100 yoctogram per gram. I had to look up the name for it, because it's so uncommon. I mean, septogram is still something which you could have, but yoctogram, it was just an incredible low number, really single atoms in your sample. And what did we find when we were looking for the curium? We didn't find anything. So there was no curium signal in our crust. And this proves that the plutonium is really old, because this can only be when the curium has decayed away with the shorter half-life, whereas the plutonium is still there. So in our case, we were modeling the curium-247 to plutonium ratio in the R process. We got the models from the R Process Alliance, thanks to Erika Hornbeck, but also we got the models from Almudena Aracones in Darmstadt. And they told us that the curium to plutonium ratio in the beginning, at the very beginning at the R process, is about 0.5. That's very roughly where it sits. But what we measure is much lower than 0.5, and that's how you then do our the timing. So for supernovae, we can exclude them because we don't see the iron-60 plutonium and curium altogether. We only see plutonium and no curium, and this tells us it must be a rare and old event. And in our case, it must be at least 70, and depending on our assumptions on the incorporation in our samples, actually the last R process near Earth must have happened more than 100 mega years ago. Then the question could be, is it primordial plutonium-244? The answer is no. We can also exclude that by measurements in other samples that are much older. We don't see any plutonium-244 in there. So it really is an influx that is coming to Earth, but it's just a very low and old influx coming from a rare and old event that only has plutonium-244 left.
Dominik, sorry to interrupt you.
Yes.
We are running a bit out of time. Ah, perfect.
Yes, I'm done. No problem at all. Yeah, just the last slide to wrap it up. I hope I could convince you that AMS is a powerful tool, usually not used for nuclear astrophysics, but also in my case, it is used for nuclear astrophysics and is actually quite powerful. We see iron-60 in 2 peaks. We have better timing now. We also see recent iron-60 from the Antarctic sample. Plutonium-244, we have a time profile now, can constrain the core collapse supernova yield quite severely. We see no curium-247, which means that the plutonium is certainly old, and we get a first time limit for a near-Earth R process event. And hopefully in the future we get more samples. We are working now on lunar samples from NASA and get a better sample and influx understanding, so we can also give better numbers for the astrophysics modelers. And with this, I want to thank you and my collaborators on this work, and happy to take any questions, and thanks for the attention.